fourth and last year graduate student at MIT, and I was ready to apply for jobs. And I was not exactly in the picture about how you go with recommendation letters. I thought, I need 3 letters. There are 3 combinatorialists at the department, so I go to them and ask a letter from each. And I ended up in the office of Giancarlo Rota, who told me that he can give me a letter, but it will not make any difference because my work is not in his field, and instead he suggests that I write to this guy, Doron Serverter. And I was a little bit surprised because we never met. I knew he had graduate students on the market, and in general, I didn't know you could ask for letters from people who don't work, who were never your professor. And then I asked Giancarlo, is he approachable? He said, I think he's pretty approachable. Which was probably the understatement of the century. So Doron did give me a letter and about 20 more as I advanced in my career. So to cut a long story short, here I am now. So yesterday many people said how So many people said how helpful Doron is with his graduate students, and I would add and with other younger people too. So thanks. So my talk is about a very specific question in the area of pattern avoiding permutations, an area in which the University of Florida has recently redoubled its approach. So Jeff Remmel came to give a talk at our department, and he talked about non-overlapping permutations, and this I will have to put into context. This is the only context I do today. Other than that, it will be one problem. There will be no big picture other than this. So we say that the permutation tightly avoids a shorter permutation if we don't have that many entries in consecutive positions. That's crucial. That's why I say tightly avoids, because they have to be in consecutive positions so that their pattern is isomorphic to Q. So here is an example. So the permutation 3, 2, 5, 1, 6, 7, 4 tightly contains the pattern 2, 3, 1 because look at the second, third, and fourth entries, and they form a 2, 3, 1 pattern. On the other hand, it tightly avoids the pattern 3, 2, 1 because you will not find 3 entries in consecutive positions so that they decrease. Even if in the classical sense, in the non-tight sense, the pattern does contain 3, 2, 1, since look at the first, second, and fourth entries, but we don't care about that. So there's a classic conjecture here by Sergi Elizalde and Mark Noy from 2001, which says that if you fix the number k and the number n, then among all patterns of length k, the one that's the easiest to tightly avoid is the monotone pattern, which is a very interesting conjecture. It's 100% surely true, but we can't prove it yet. But what's interesting about this is that it is not the same thing as for the classical patterns. For classical patterns, the monotone pattern is close to be the easiest to avoid, but it is not the easiest to avoid. So there is something fundamentally different between tight.
You quote it, right?
I had the first count, for example. Right. So there is something fundamentally different between tight pattern avoidance and traditional pattern avoidance. So as far as I know, there was not much progress on this conjecture since 2001, until again Jeff Remmel came to Florida this March, and he gave a talk about non-overlapping permutations. So this is the definition for today. So if you think you will pay attention for 1 minute, then make this 1 minute. otherwise the rest of the talk is lost. So we call a permutation non-overlapping if 2 copies of it cannot overlap in more than 1 entries. And then, you know, and if you choose any permutation pattern, you can take 2 copies of it so that the last entry of the first copy is the same as the first entry of the second copy. You can always do that. But for some permutation, you can only do that and not more. Like look at 1, 3, 2. So that is non-overlapping, because if you want to take an other copy of 132, then you cannot start it earlier than on the last entry of 132, right? You cannot start it on the 3, because then you will be forced to go down in the first move, whereas you want to go up. On the other hand, 2143 is not non-overlapping, it's overlapping, because to take that permutation, right, it contains of 2 overlapping copies of 2143, then the first 4 entries and the last 4 entries. Is this clear? Okay, so this is our definition. So Jeff Remmel gave a talk about his results with a co-author, which did not contain anything about the Elizalde-Noy conjecture, but it did contain some formulas for these for the number of these non-overlapping patterns. Not overly nice formulas, but also not overly disgusting ones. So something you could work with it. It's really important for you. And so after his talk was over, I asked him if these formulas imply the solution of the Elizalde-Noy conjecture, which is again that the monotone pattern is the easiest to avoid, for the non-overlapping patterns, and he said yes. I was a little bit surprised that, you know, if he did such a great thing, then why was it not in the talk? But if you think about it, you are comparing apples and oranges, because he had some formulas which were not, which involved summation, but they were still formulas for these numbers. On the other hand, for the monotone patterns, the number of permutations of length n avoiding a monotone pattern for a given length is not known in the sense of a formula. It's known, a generating function is known, and then you can extract the coefficients. And the generating function is not the simplest either. So it's probably not so easy to compare those numbers, but it's probably possible. So this gave my motivation, which is, okay, so we can solve this great conjecture for these patterns. How many such patterns are there? So how big a fraction of the Elizalde-Noy conjecture is solved? Okay, how many patterns of length n are non-overlapping? And the following crude lower bound is encouraging. It tells you that if you do almost nothing, you can already show that quite a bit. Because let's do this. Let's count how many permutations of length n are overlapping. So if a pattern is overlapping, that means that there is some I, so that the first I entries of the permutation and the last I entries are identical, because that's when you can overlap the first I with the last I.